Why does a glass of ice water feel like the definition of cold when, on the cosmic scale, that liquid is actually screaming hot? The ice sits exactly 273 degrees above a limit nature has set in stone. This boundary is absolute zero, a point where the fabric of reality shifts. For centuries, scientists believed this was merely a theoretical line on a chalkboard. They were wrong in 2021. Researchers at the University of Bremen in Germany achieved a temperature of 38 picokelvins. That is just 38 trillionths of a single degree above the limit. The team dropped a cloud of magnetized gas down a 120-meter tower, allowing the atoms to fall into a state of near total stillness for 2 seconds. In that brief window, they created one of the coldest spots in the history of the cosmos. Temperature is not a sensation. Physics defines it as speed. Every atom in your body, your chair, and the air around you is vibrating. Even in a frozen block of lead, the atoms dance with restless energy. Heat is the measurement of that jittery motion. As they move faster, the object feels hotter. As they slow, it cools. This leads to a haunting realization. There must be a point where the dancing stops and the scale hits a floor where every atom sits still. This is the wall at the end of the world. It sits at -273. 15 degrees Celsius. Nothing can ever be colder than this because you cannot have less motion than standing perfectly still. Lord Kelvin first mapped this territory in 1848. While working at the University of Glasgow, he realized science required a scale starting at the absolute bottom. He called this point zero. On his scale, the freezing point of water is a relatively balmy 273 degrees. But as researchers raced toward that zero, they found that nature guards its secrets with terrifying efficiency. As you remove heat, the world breaks. Common materials transform into something unrecognizable. Rubber becomes as brittle as glass and shatters under a feather's weight. Air turns into a liquid that pours like water before freezing into a solid block. By the time you get within a few degrees of the limit, the rules of daily life simply stop applying. The quest to reach this point became a high-stakes scientific drag race. In 1908, a Dutch physicist named Heike Kamerlingh-Ons spent years trying to turn helium gas into a liquid. Helium is the most stubborn element on the periodic table, refusing to liquefy until it is just 4 degrees above absolute zero. When Ons finally succeeded in his Leiden lab, he found a doorway to a new reality. He discovered that at these extreme lows, electricity can flow through a wire forever without losing a single drop of energy. He had discovered superconductivity. It was the first hint that when things get this cold, the universe stops acting like a machine and starts acting like a ghost. There is a catch that prevents us from ever winning the race. A German chemist named Walther Nernst proved in 1906 that reaching absolute zero is physically impossible in a finite number of steps. Think of it like trying to walk halfway to a wall, then halfway again, and then halfway again. You get closer and closer, but you never actually touch the brick. You can get to a millionth of a degree, a billionth, or even a trillionth, but that final zero remains out of reach. Nature seems to abhor a vacuum of motion. The universe has a built-in speed limit at the top, which is the speed of light, and a stillness limit at the bottom. If you could somehow stand in a room at absolute zero, you would witness the death of chemistry. Chemical reactions require atoms to collide and swap electrons. But at the bottom of the scale, there is no collision. Time would appear to stop for the matter involved. However, even in this total stillness, a strange humming anxiety remains. Quantum mechanics tells us that even at the absolute floor, particles still have a tiny bit of zero-point energy. They can never be 100% motionless. The universe vibrates at its core, even when it is frozen solid. The most incredible part of this journey is what happens to the atoms right before they hit the wall. In 1995, Eric Cornell and Carl Wieman used lasers to trap rubidium atoms and sap their energy until they were just a fraction of a degree above zero. Suddenly, the individual atoms lost their identities. They stopped acting like separate little balls and merged into one single superatom. Thousands of atoms began to act as if they were a single heartbeat. This is the Bose-Einstein condensate. It is a fifth state of matter that doesn't exist anywhere in the natural world except in our most advanced laboratories. When we push matter to these limits, we see things that look like magic. We see superfluids, liquids that have zero friction. If you put a superfluid in a bowl, it will literally crawl up the sides of the container and leak out over the edge. It defies gravity because it has no internal resistance to hold it back. It can flow through holes so small that even a single molecule of air couldn't pass through. This is the deeper layer of the mystery. Absolute zero isn't just a number on a thermometer, but a place where the physical objects we touch every day reveal their true, wavy quantum nature. Scientists are now using these ultra-cold environments to build the computers of the future. Quantum computers rely on the strange stillness of near-zero temperatures to perform calculations that would take a normal computer a billion years. We are finding that the colder we get, the more powerful our technology becomes. We are leaning into the silence at the bottom of the world to listen to the fundamental code of the universe. The tower in Bremen, where they dropped that magnetized gas, is just the beginning. We are learning how to manipulate the very building blocks of existence by simply making them stop moving. The next time you feel a winter wind or touch a piece of ice, remember that you are only feeling the surface of what cold can be. Deep in the basement of physics, there is a silence so profound that it changes what it means to be a physical object. We are travelers on a journey toward a destination we can never officially reach. We are peering over the edge of a cliff that marks the end of motion itself. We are going to see how reaching this limit doesn't just make things cold. It breaks the laws of physics, allowing liquids to flow uphill and atoms to occupy the same physical space at the same time. This transition reveals the true stakes of the experiment. Why can we never reach the bottom of the temperature scale? To find the answer, we must redefine what heat actually is. In our daily lives, we treat heat as a sensation, like the warmth of a radiator or the sting of a sunburn. But in 1848, a physicist named William Thomson, better known as Lord Kelvin, realized that heat is something much more fundamental. Working at the University of Glasgow, he proposed a new way to measure the world. He realized that temperature is a measurement of how fast the tiny particles inside an object move. When you touch a hot cup of coffee, the molecules inside are vibrating and crashing into each other like a room full of frantic dancers. When that coffee cools, those dancers are simply slowing their pace. Kelvin realized there must be a point where the dancing stops entirely. He called this point absolute zero. It is the theoretical basement of the universe, calculated to be minus 273, 15 degrees Celsius. Physics takes a strange, frustrating turn at these extremes. As scientists began racing toward this basement, they hit a wall built into the logic of reality. In 1906, a chemist named Walther Nernst was working at the University of Berlin when he formulated the third law of thermodynamics. Nernst discovered a mathematical rule that acts like a cosmic speed limit in reverse. His work showed that as you get closer to absolute zero, it becomes exponentially harder to remove the next tiny bit of heat. Think about trying to dry a damp floor with a sponge. A bone-dry sponge soaks up water easily. As the sponge gets wetter, it loses its ability to hold more. In this world, your cooling equipment is the sponge. To draw heat out of an object, your equipment must be colder than the object itself. But to cool the equipment, you need something even colder than that. This creates a paradox that has haunted laboratories for over a century. Every time a scientist tries to measure a temperature near absolute zero, they face a fundamental problem. The act of measuring adds heat. Imagine trying to see if a dark room is empty by shining a flashlight inside. The moment you turn on the light, you change the state of the room by filling it with photons. In the cryogenics lab, a tiny vibration from a pump or a single grain of dust carries enough energy to warm up a cluster of atoms by 1,000 degrees in their world. The third law of thermodynamics states that you can reach the neighborhood of absolute zero, but you can never walk through the front door. You can get to 0.00001 degrees, and then 0.0000001 degrees. That final step to a perfect zero requires an infinite amount of work. Despite this impossible barrier, the race to the bottom became the greatest engineering challenge of the 20th century. In July 1908, a Dutch physicist named Heike Kamerlingh-Onnes sat in his lab at the University of Leiden, surrounded by hissing pipes and shimmering glass tubes. He was trying to do something many thought was impossible by turning helium gas into a liquid. Helium was the last permanent gas, a substance so stubborn it refused to liquefy even at the coldest temperatures known. Onnes spent years building a complex machine that functioned like a giant, high-tech refrigerator. When he finally succeeded, he reached a temperature of just 4.2 degrees above absolute zero. It was a landmark moment that earned him a Nobel Prize. It also revealed something unsettling. Matter did not just get colder. It started to break the rules of classical physics. When Kamerlingh-Onnes looked at his liquid helium, he noticed it behaved in ways that defied common sense. This was further explored in 1938 by Piotr Kapitsa in Moscow and John F. Allen in Cambridge. They discovered a phenomenon called superfluidity. When helium is cooled below a specific point, it loses all internal friction. If you put it in a beaker, it will literally crawl up the sides of the glass and flow over the edge to find a lower point. It can leak through holes so small they are airtight. The atoms stopped acting like individual marbles and started acting like a single, unified wave. This was the first hint that near the bottom of the scale, the universe stops being a collection of distinct objects and starts behaving like a giant, shimmering ghost. Satyendra Nath Bose and Albert Einstein predicted the reason for this ghostly behavior decades earlier. They theorized that if you could get atoms cold enough, they would lose their individual identities. They would overlap and merge into a single superatom. This state of matter is now known as a Bose-Einstein condensate. For 70 years, this was just a math problem on a chalkboard. No one could build a refrigerator powerful enough to prove it. The problem was that traditional cooling using liquids and pumps could only go so far. To go deeper, scientists had to stop using mechanical force and start using something much more precise. Light. It sounds counterintuitive to use a laser to cool something down. But in the 1990s, researchers figured out how to use the pressure of laser light to hit moving atoms head-on, forcing them to slow to a crawl. In June 1995, Eric Cornell and Carl Wieman at a laboratory in Boulder, Colorado finally broke through. They used a combination of lasers and magnetic fields to trap a small cloud of rubidium atoms. By carefully shaving away the fastest, hottest atoms, they allowed the remaining ones to settle into a deep, quiet chill. They reached a temperature of just 170 nanokelvins, which is 170 billionths of a degree above absolute zero. At that moment, the atoms collapsed into the state Einstein had predicted. They became a single quantum blob large enough to be seen under a microscope. This was not just a cold gas. It was a new form of existence. The researchers had successfully pushed matter to the very edge of the third law barrier, creating a place in a Colorado basement that was colder than the deepest reaches of interstellar space. The achievement was so significant that the Nobel Committee awarded them the prize in 2001. But the quest did not end there. If 170 billionths of a degree was possible, scientists wondered how much further they could go before the universe pushed back. In 2003, Wolfgang Ketterle's team at MIT pushed the record down to 450 picokelvins. To put that in perspective, if you represented the distance from room temperature to absolute zero as a trip from New York to San Francisco, these scientists were now within a hair's width of their destination. They were operating in a realm where the standard laws of chemistry simply evaporate. In this deep cold, chemical reactions that usually happen in a fraction of a second can take minutes. Sometimes they do not happen at all. Why does the universe have a bottom at all? This brings us to a fundamental question about the nature of our reality. We know there is no absolute hot in the same way. As you can keep adding energy to a plasma until stars collapse and holes rip in spacetime. But at the cold end, there is a hard stop. A wall. Scientists like Lev Landau spent their lives trying to map the strange physics of this frozen frontier. They realized that as motion dies away, the weirdness of quantum mechanics takes over. In this quiet zone, atoms can be in two places at once, and information can be shared across distances instantly. The closer we get to the stop sign of absolute zero, the more we realize that stillness is not what we thought it was. Even when the dancing stops, the dancers are still there, vibrating with a ghostly energy that can never be removed. We have now reached a point where we can create temperatures so low they make the vacuum of space look like a furnace. The Boomerang Nebula, the coldest known natural place in the cosmos, sits at 1 degree above absolute zero. In our labs, we are now millions of times colder than that. We have built the coldest spots in the known universe right here on Earth. But as we stare at that final, unreachable zero, we have to wonder what happens to the atoms themselves. If we could somehow cheat the third law and remove that last pulse of energy, would the matter simply vanish? Or is there a final secret hidden in the stillness that our current laws of physics are not yet ready to explain? The answer lies in what happens when we try to look at something that has truly, finally stopped moving. Could a finish line recede with every step? By 1908, the world of science was racing toward a boundary that seemed to pull further away the closer they got. At the University of Leiden, Heike Kamerlingh-Onnes finally managed to liquefy helium by reaching a temperature just 4 degrees above the absolute bottom. This victory opened a door to a reality that defied every known law of physics. When matter gets this cold, it does more than just freeze into a solid. It transforms into a state that looks and acts like a ghost. Scientists discovered that near the absolute zero mark, the atoms themselves begin to lose their individuality. They stop behaving like distinct little billiard balls and start acting like a single, unified wave. Imagine a crowded stadium where every person suddenly dissolves and merges into one giant, shimmering organism moving in perfect unison. In 1924, a young Indian physicist named Satyendra Nath Bose sent a paper to Albert Einstein describing a new way to count particles. Einstein was captivated. Together, they predicted a fifth state of matter, now called a Bose-Einstein condensate. They realized that if you could get atoms cold enough, they would all fall into the lowest possible energy state. At this point, the identity of a single atom vanishes. You no longer have a billion separate particles. Instead, you have one superatom that occupies the same space at the same time. It was a radical theory that waited 70 years for a laboratory to catch up to the imagination. The breakthrough finally arrived on June 5, 1995. At a laboratory in Boulder, Colorado, Eric Cornell and Carl Wieman were working with a tiny cloud of rubidium atoms. They used lasers to push against the atoms to slow them down, and then used a magnetic trap to evaporate the warmest ones away. When they reached 20 billionths of a degree above absolute zero, the unexpected happened. The atoms didn't just sit there. They suddenly collapsed into a single, dense blob that moved as one. It was the first time humans had ever seen this fifth state of matter. The discovery earned Cornell and Wieman the Nobel Prize in 2001. But the strangest part was how the atoms started to move. When matter reaches these extreme lows, it becomes a superfluid. In 1938, Pyotr Kapitsa in Moscow and John Allen in Cambridge both noticed something impossible about liquid helium. If you put this liquid in a glass beaker, it begins to crawl up the sides of the glass, defying gravity, and flows over the edge. If the container has holes so small that even air cannot pass through, This liquid will leak right through the bottom as if the solid walls weren't even there. This happens because the atoms have lost all friction. They no longer rub against each other or the walls of the container. They flow with zero resistance. To put that in perspective, if you stir a cup of coffee, the liquid eventually stops spinning because of friction. But if you could create a whirlpool in a superfluid and then leave it alone, it would keep spinning forever. It would literally never stop. In 1941, Lev Landau explained that this happens because the entire liquid is behaving like a single quantum wave. There is no internal rubbing to slow it down. It is a perfect machine with no lost energy. Scientists at MIT, led by Wolfgang Ketterle, later took this even further. In 2003, they cooled sodium atoms to 450 picokelvins, which is less than half a billionth of a degree from the edge of the universe's hard floor. At these depths, the rules of our daily lives simply evaporate. We are used to a world where things have edges and boundaries. You cannot walk through a wall, and your coffee doesn't climb out of the mug. But in the world near absolute zero, the ghost in the machine takes over. Because the atoms are waves. They can overlap, they can be in multiple places at once. This is the result of reaching a temperature so low that the chaos of heat no longer drowns out the strange music of quantum mechanics. In these labs, researchers are witnessing the rawest form of reality, where matter is more like a haunting melody than a solid object. But here is where it gets even stranger. If these atoms are all behaving like a single wave, they can do things that should be physically impossible. In some experiments, researchers have found that light itself, which usually travels at 186,000 miles per second, can be slowed down to the speed of a bicycle when it passes through a Bose-Einstein condensate. In extreme cases, they have even managed to stop light completely, trapping it inside the superatom and then releasing it later. We are talking about freezing the fastest thing in the universe in its tracks, simply by removing the vibration of heat. Consider the implications, because this frictionless state is the key to technologies we have only dreamed of. If we could harness this zero-resistance flow at higher temperatures, we could create power lines that never lose a single watt of electricity or trains that float on magnets with zero energy loss. But for now, these miracles only happen at the very edge of the abyss. The closer we get to the absolute bottom, the more we realize that matter isn't what we thought it was. It is much more fluid, much more connected, and much more mysterious than the solid world suggests. Scientists still can't fully explain why some materials become superconductors at slightly higher temperatures while others require the extreme cold of a picokelvin. The quest to reach the bottom has turned into a quest to understand the very fabric of existence. We are looking at a state of matter that shouldn't exist according to our common sense. Yet it is there, sitting in a vacuum chamber in a basement in Colorado or Germany. It is a reminder that, when you take away the noise of heat, the universe reveals a hidden, quiet order that operates on a logic we are only just beginning to map. Every time we shave another billionth of a degree off the record, the superatom becomes more stable, and its behavior becomes more bizarre. We have reached a point where we can manipulate the very essence of matter as if it were clay. But as we continue to push toward that final, unreachable zero, a new question emerges. If absolute zero is a wall that can never be touched, what happens to the laws of physics as we get infinitely close to it? Does the universe have a final secret waiting at the very end of the cold? Or does the scale simply go on forever into a darkness we can't yet imagine? Could the coldest place in the natural universe exist far beyond the reaches of our solar system? Astronomers usually point their telescopes toward the Boomerang Nebula, a massive cloud of gas 5,000 light-years away where the temperature sits at a brutal 1 degree above absolute zero. For a long time, we believed this was the ultimate floor. It was the basement of existence, a place so frozen that nothing could ever possibly get colder. But in 2021, a team of researchers at the University of Bremen in Germany decided they could do better than nature. They ignored distant stars and frozen moons to focus on a 120-meter tower made of concrete and steel. Inside this drop tower, they prepared to break a record that seems to defy the laws of the physical world. Their goal was to reach a depth far beyond the cold of deep space. Ernst Racel and his colleagues started with a tiny cloud of 100,000 rubidium atoms. At room temperature, these atoms are a chaotic swarm, buzzing around at hundreds of miles per hour. To stop them, the team used a specialized magnetic lens. Think of it like a pair of invisible hands that gently squeeze the atoms from every direction, forcing them to settle down. But even this wasn't enough to reach the record. They needed to remove gravity, the one force that ruins almost every physics experiment on Earth. To do this, they loaded their experiment into a capsule and dropped it from the top of the tower. For 2 seconds, the experiment was in total freefall. In that brief window of weightlessness, the team manipulated the magnetic fields to trick the atoms into standing almost perfectly still. The rubidium atoms were barely existing. When the sensors finally crunched the numbers, the result was staggering. The team had reached a temperature of 38 picokelvins. To put that in perspective, a picokelvin is 1/trillionth of a degree. This means the Bremen team was just 38 trillionths of a degree away from absolute zero. It is a number so small that the human mind struggles to visualize it. If you compared this temperature to the freezing point of water, the difference would be like comparing the width of a human hair to the distance between the Earth and the Sun. In that moment, a small patch of gas in northern Germany became the coldest known spot in the entire universe. It was significantly colder than the Boomerang Nebula and the dark voids between galaxies. Human beings are now creating environments that the universe itself cannot produce on its own. The story gets strange at these extreme depths because the rules of reality start to break. We usually think of atoms as little billiard balls bouncing around. However, at 38 picokelvins, they stop behaving like individual objects and merge together into a single giant superatom known as a Bose-Einstein condensate. This state of matter was first predicted by Albert Einstein and Satyendra Nath Bose in 1924. But it took 70 years for anyone to actually see it. In this state, every atom in the cloud starts to act in perfect unison. If one atom moves, they all move. They become a single wave of matter, flowing with zero friction and zero resistance. It is a hauntingly quiet version of reality where the frantic energy of life simply vanishes. This achievement in the Bremen Drop Tower wasn't just about bragging rights or breaking a world record. Scientists still can't fully explain why matter behaves so strangely when it nears the absolute floor. When the atoms were dropped, they stayed in this ultra-cold state for 2 seconds. That might sound like a heartbeat, but in the world of particle physics, it is an eternity during those 2 seconds. The researchers observed the atoms expanding in slow motion, like a ripple in a pond that refuses to disappear. By reaching 38 picokelvins, they opened a door to a version of the universe that is usually hidden by the noise of heat. They created a window into the very foundations of how space and time interact with matter. There is a terrifying realization that comes with this level of cold. To reach 38 trillionths of a degree, the researchers had to fight against the entire universe. Heat is the natural state of things. It is the energy that keeps stars burning and hearts beating. By stripping that energy away, we are creating a void that is more empty than a vacuum. Some physicists believe that if we could actually reach absolute zero, the atoms might simply cease to occupy a specific place in space. They would become so spread out that they would exist everywhere and nowhere at the same time. We are poking at the very edge of what it means for something to be real. The closer we get to the bottom of the scale, the more the material world seems to dissolve into math and probability. While the University of Bremen currently holds the record for the lowest temperature ever recorded, they are already looking for ways to go lower. There are plans to bring these experiments into orbit, using the International Space Station to achieve even longer periods of weightlessness. in space without the jar of the capsule hitting the ground. Scientists think they can keep atoms at these temperatures for minutes instead of seconds. They want to see if there is a point where the laws of physics finally snap. If we can reach 5 picokelvins, or 1 picokelvin, what happens to the matter? Does it change into something we haven't even named yet? We are currently building the coldest machines in history to answer questions we didn't even know how to ask a century ago. Consider the reason this matters beyond a simple lab trick. The precision required to measure 38 picokelvins is the same precision needed to build the next generation of technology. These ultra-cold atoms are the heart of quantum sensors that can detect tiny changes in gravity or magnetic fields. They could allow us to map the interior of the Earth in high definition or detect the faint ripples of gravitational waves from the other side of the cosmos. But every step closer to the 0 point requires an exponential increase in effort. It is like trying to reach the horizon. You can see it, you can walk toward it. But the faster you move, the further away it seems to get. The third law of thermodynamics acts like a cosmic speed limit, forbidding us from ever truly touching the bottom. Think about the sheer isolation of those rubidium atoms in the tower. For 2 seconds, they were separated from the rest of the warm, vibrating universe. They were in a state of stillness so profound that it shouldn't exist. If the universe is a symphony of motion and heat, these experiments are the only places where there is total silence. But that silence is fragile. The moment the capsule hits the brakes at the bottom of the tower, the heat of the world rushes back in. The atoms begin to shake. The superatom dissolves and the record-breaking cold vanishes in a puff of thermal energy. We can visit the bottom of the scale, but we can never stay there. This leaves us with a bleak concrete beat. We have spent decades and millions of dollars to build a tower that can produce a temperature colder than the deepest void of space. We have successfully outcooled the universe. Yet despite all our magnets, lasers and towers, we are still staring at a wall we cannot climb over. We can reach 38 trillionths of a degree, but that final tiny gap, that last sliver of temperature, might as well be a billion miles wide. We are standing at the edge of a cliff, looking down into a darkness that we can measure but never truly enter. The question is no longer how cold we can get, but what is waiting for us in that final, unreachable shadow at the very bottom of the world. Can a computer solve a problem in seconds that would normally take a billion years? This impossible speed is the prize for mastering extreme cold, a feat that goes far beyond laboratory tricks or record-breaking numbers. When you look at a quantum computer, you see a towering chandelier of gold and copper wires. Its true heart, however, is a small chip kept at the edge of absolute zero. This extreme environment allows atoms to act in ways that defy everyday logic, enabling particles to exist in 2 places at once or link together across vast distances. Google and IBM are betting billions on this stillness. They need that deep artificial silence to build machines capable of simulating new life-saving medicines or creating materials that have never existed in nature. Without the stillness found near the absolute zero wall, the noise of heat would simply be too loud for these machines to function. Think about the smartphone in your pocket to put this in perspective. It is a miracle of engineering, but it is also incredibly inefficient. As electricity flows through its circuits, it bumps into atoms, creating friction that we feel as heat. This heat is wasted energy, a tax we pay for every second of use. In the world of the ultra-cold, that friction can vanish. This is the promise of superconductors, materials that allow electricity to flow forever without losing a single spark of power. Researchers at the University of Leiden and beyond have spent decades searching for a material that works this way at room temperature. If we can bring the magic of the absolute zero lab into our power grids, we could transport energy across entire continents with zero loss. The coldest places in the universe are workshops for a new industrial revolution rather than empty voids. You can see the fingerprints of this research in your daily life already. Every time a doctor uses an MRI machine to look inside a patient's body, they are using the power of the cold. Those machines rely on massive magnets cooled by liquid helium to 4 degrees above absolute zero. Without that cooling, the magnets would melt under their own power. The technology that helps diagnose a broken bone or a hidden tumor is a direct descendant of the race to reach the bottom of the scale. These abstract experiments in physics eventually find their way into hospital rooms and living rooms. We are not just exploring the cold for the sake of curiosity. We are harnessing it to see the invisible. Even as we build these incredible tools, we are forced to confront a limit that cannot be broken. Walther Nernst proved over a century ago that we can get closer and closer to the bottom, but we can never actually touch it. It is like a runner who cuts their distance to the finish line in half with every step. They get incredibly close, but they never actually cross the line. This realization changed how we view the universe by showing us there is a floor to reality. This is a point where the dance of existence almost stops but never truly dies. Even in the deepest reaches of space, there is a tiny, flickering pulse of energy. The universe refuses to be perfectly still. Our struggle to reach absolute zero has taught us that the world is not made of solid, predictable billiard balls at the lowest temperatures. The boundary between one object and another begins to blur. We have discovered that when you take away the heat, you reveal the true, wavy nature of reality. This is a fundamental truth about what you are made of. Your body is a chaotic, buzzing hive of trillions of moving parts, all vibrating with the heat of life. We only understand that vibrant motion because we have seen what happens when it is stripped away. The cold is the mirror that allows us to see the true nature of energy. Try a simple experiment tonight if you want to feel the scale of this for yourself. Look at a glass of water and think about the molecules inside. They are tumbling, spinning, and crashing into each other at hundreds of miles per hour. Then think about those researchers at the University of Bremen in 2021. For 2 brief seconds, they managed to make a cloud of gas almost perfectly still, reaching 38 trillionths of a degree above the limit. In that moment, those atoms were the quietest things in the known universe. They were more still than the heart of a void between galaxies. That contrast between the heat in your hand and the stillness in that lab is one of the widest gaps in all of nature. Scientists still can't fully explain why the universe has this specific speed limit at the bottom. We know the math and the rules, but the why remains a great lingering mystery of physics. Some theorists suggest that if we could ever truly reach absolute zero, the laws of physics might simply break down. It is a wall that protects the integrity of the cosmos. By trying to crack that wall, we are testing the very boundaries of what is possible. Every fraction of a degree we descend reveals a new layer of complexity that was hidden by the glare of heat. The deeper we go, the more the universe reveals its strangest secrets. As we stand at the edge of this absolute zero wall, we realize that these hard limits are actually doorways. Mastering the cold has given us the ability to keep time with atomic clocks that won't lose a second in millions of years. It has given us sensors so sensitive they can detect the tiny ripples in space caused by colliding black holes. None of this would be possible if we hadn't decided to chase a number that we knew we could never reach. It is a testament to the human spirit that we spent 200 years pursuing a goal that is theoretically impossible. We didn't get to zero, but in the process, we found everything else. Next time you feel a winter chill or hold a piece of ice, remember that you are part of a very warm, very loud world. You are trillions of times warmer than the strangest, most advanced places on Earth. We live in the thin, hot crust of a universe that is mostly cold and silent. But it is within that silence that the most incredible things happen. We have learned to use the stillness of the atoms to build the future, turning the coldest limit of nature into the hottest frontier of technology. The wall at the bottom of the scale isn't a dead end. It is the foundation upon which the next century of human discovery will be built. Imagine the universe as a vast, Dark ocean, where we have finally learned how to dive deep enough to see the creatures at the bottom. We cannot stay there forever, and we cannot touch the floor. But the view from the depths has changed our understanding of the surface forever. The stillness of absolute zero is the ultimate quiet. A silence so profound that it allows us to finally hear how the universe actually works. As we continue to push against that final degree, we are not just cooling down matter. We are warming up to the true potential of the human mind. The journey to the bottom is just beginning.